Hi everyone. This is Dr.G Ramakrishna, an assistant professor from Computer Science and Engineering Department, IIT Tirupati. In this work, I am going to present our algorithm on short fastest path problem in temporal graphs. Here is the outline of our presentation. We start with few definitions such as temporal graph, short fast path problem, and so on. And further, we go and present few of our past results. Then we move on to our algorithm on short fastest path problem. And finally, we are going to conclude this presentation with few key lemmas and theorems. Here is an example of a temporal graph in which every edge is associated with two parameters such as t and lambda, where t denotes the departure time of a vehicle starting at a vertex, say u, whereas lambda denotes the duration time from u to v. Here we are going to define few important terms such as travel time and waiting time. Consider there is a journey from x1 to x4 using this temporal graph or public transportation. The amount of time that we spent in a vehicle is referred to as travel time. The amount of time that is spent at intermediate stations is called waiting time. Now, when we perform the summation on these two terms, essentially the summation of travel time and waiting time is referred to as journey time. Now let us look at lot of paths from a source vertex to a destination vertex. Among all such paths, the path whose journey time is minimum is referred to as fastest path, whereas if we choose a path whose travel time is minimum, such a kind of path we refer to as shortest path. In this work, we are interested in short fastest paths, which means we want to choose a fastest path whose travel time is minimum. From the past work, from the literature, we know that there is a linear time algorithm for earliest arrival path problem, and also there are near linear time algorithms available for fastest path problem and as well as shortest path problem. In our work, right, we are focusing on short fastest path problem in this presentation. As part of the input, we are going to get a temporal graph G and as well as a source vertex S. The main focus of this problem is to compute journey time and as well as travel time of short fast path for all the rest of the vertices from the given source vertex S. Coming to our main result, our main result is we have designed an efficient algorithm to solve short fast path problem, and the running time of our algorithm is order of n plus m times log of pg, where n denotes the number of vertices, m denotes the number of edges, and p of g denotes where p of g is at most the maximum over all edges, maximum over travel times of all edges. Now we are going to define the relation called domination. Consider there are two paths between two vertices, say x and y. We say that a path P is better than Q in some sense. In other words, we say that P dominates Q if it satisfies one of the three following conditions. The three conditions are listed here. As per case 1, P starts after Q, P starts after Q, but whereas P ends on or before Q. This is case 1. Whereas case 2, both P and Q starts at same time and further P ends before Q. On top of this, we have another constraint where the travel time of P is at most the travel time of Q. As per case 3, The starting time of both P and Q is same, and at the same time the arrival time of P and Q are also same. And then further the additional constraint is the travel time of P or the duration time of P is strictly less than the duration time of Q. If P, if we say that P dominates Q if it satisfies one of these three following conditions. This is one of the key idea or major idea in our algorithm. In our algorithm to compute the short fast path. Consider there is a source vertex S. From S to any arbitrary vertex say V, rather than storing all paths, we are interested to compute only dominating paths without affecting the correctness of our algorithm. In a sense that the dominating paths will be enough to get the results. So what do you mean by dominating paths? So dominate a path is said to be dominating path if this particular path is not dominated by any other path. So such kind of paths we are interested in, and these kind of paths will be enough to get the results. Now we are defining the concept of dominating triples. The concept of dominating triples will be useful to quantify or to store the vital information of dominating paths. In a sense, if there is a dominating path from x to y, the vital parameters are starting time and as well as arrival time, which is nothing but t3 plus lambda 3, and the total travel time of this whole journey, the total travel time is nothing but lambda 1 plus lambda 2 plus lambda 3 without including waiting times. So these three parameters such as starting time, arrival time and duration time is going to be useful to store every dominating path. Such triple we are calling as dominating triple. Now we are describing the overview of our algorithm. As per our algorithm is concerned, we are going to process all the edges in increasing order based on their departure time. Whenever we go and process the current edge, with respect to every edge we are going to perform three major steps. At each vertex say u and v and so on, at every vertex we are going to maintain a list of dominating triples. At each vertex we are going to maintain these list of dominating triples. Now when we discuss about these three steps, the first step is whenever we are looking at the current edge say ei, with respect to ei, we need to choose among all these triples, we choose one predecessor triple, which is nothing but among all these journeys we are going to choose one partial journey and going to combine this partial journey with the current edge and create a new journey or new triple. So in a sense we are going to extract a partial journey, creating a new journey and inserting this new journey into lv. This is what the major overview of our algorithm. Now we are going to discuss all these three steps in detail. This is one of the most important slide in our whole presentation. This is the concept of choosing a predecessor triple. Now consider that we are processing this edge from u to v whose travel time is lambda and the departure time is t. If at all we want to extend certain journeys that are available in LU by using this new edge, if at all we go through all these triples, among all these journeys, there are few journeys which are shown in red color which cannot be extended because their arrival time is greater than the departure time of the current edge. Whereas there are few more journeys which are shown in blue color can be extended. Among all such journeys, the one whose arrival time is maximum is referred to as predecessor triple. And we are interested to compute this find out this predecessor triple for extending the partial journeys. So once we choose such kind of predecessor triple, this predecessor triple we are denoting as S3 A3 D3 in this example. So this is the predecessor triple and this is our current edge. This predecessor path and as well as the current edge, if we combine both of them, we are going to obtain our new journey. Our new journey's starting time is S3 and arrival time is t plus lambda, and the duration time, which is nothing but the total travel time, d3 plus lambda, can be obtained from these two paths. Once we obtain this new triple, of course the new triple can be obtained in constant time. Once we obtain this new triple, now as part of our third step, we have to make sure before we insert this new triple into LV, we try to verify that whether this new triple, if whether this new triple dominates one of the existing triples in LV, or this triple itself is dominated by few of the triples in LV. If one of these if one of these two things happen, we have to make sure to delete these unnecessary triples and maintain only dominated triples by the time we go to the next iteration. Of course, once we perform these three steps on all the edges, now we will be left with only dominating triples at all vertices, and then we can compute journey times and as well as travel times by going through all these dominating triples at each vertex. Now, if we observe the kind of algorithmic challenges, the way if we recall the three steps what we have seen so far: extracting a predecessor triple, creating a new triple, and inserting the new triple in LV. Among all these three steps, the second step is a trivial one in a sense which takes constant time, whereas the first step and the third step or non-trivial steps. So in a sense, these are our algorithmic challenges in our work. So in order to resolve these algorithmic challenges, we have come up with these two ideas. The first one is we have processed all the edges in increasing order based on their arrival times rather than departure times. This is our key idea as a first idea. Then as per our second idea, rather than maintaining all these triples, all these dominating triples in some arbitrary order in every vertex, the list associated with every vertex, we maintain all these triples in lexicographic order, which means arrange all of them in increasing order based on their starting time and as well as arrival time. Based on these two key ideas, once we implement these two key ideas, then based on this, we were able to choose a predecessor triple from LU in order of log PG time. And similarly, if you want to insert or delete certain triples in LV, still we are able to do in a constant time. Based on these two key ideas, and further we are going to process these three steps on every edge. So because of this, the total running time of our algorithm will be bounded by n, which denotes the number of vertices, plus the total number of edges multiplied by log p of g, which is the critical factor for choosing a suitable or predecessor triple. This is how the runtime analysis gets completed for our algorithm. Now, if we look at the key lemmas, one of the key lemma in our work is prefix subpath lemma, where as per this lemma, if you look at every dominating path, or if you look at any dominating path, every prefix subpath, every prefix subpath of this dominating path is also dominating, and this property holds for dominating paths the way we have defined. Whereas if you look at this kind of lemma is not true for fastest paths and as well as shortest paths. This is one of our major theorem which helps us to act as a loop invariant for our algorithm. As per this theorem, if you look at GI denotes GI is nothing but the graph formed on first I edges. Once we are clear with this GI, now we look at the dominating triples. All dominating triples in GI from source vertex S to any arbitrary vertex phi, all such kind of dominating triples in GI are precisely stored in Ly after ith iteration gets over. And after ith iteration gets over, we are not going to store any more number of triples or nor lesser number of triples. The triples whatever we store in our algorithm in Ly after ith iteration should be precisely equal to the triples that are available in GI. So this theorem we have proved, and this theorem is going to helpful, or this theorem is actually acting as the proof of correctness for our algorithm. In a nutshell, in a sense that we have three key ideas we have used in our work, where the domination relation helps us to design an algorithm. The lemma on prefix paths helped us to prove the correctness of our algorithm, whereas the third one, lexicographic ordering of maintaining triples, helped us to increase the running time of to improve the running time of our algorithm to solve shortest to solve short fastest path problem. Thank you. Thank you for all the organizers.